Okay, so lecture 14. Today we are going, in this first hour, we are going to apply what we learned about Riemannian manifolds to optimization problems. So, first of all, it should be clear that given the Riemannian gradient descent algorithm we studied for submanifold over n, we can reproduce the same setting on a general Riemannian manifold once we have a retraction. And, for example, the exponential map we saw is a retraction. But, I mean, there are a number of them, so actually finding a retraction from the tangent on the manifold usually is not a problem. So once we have that, and we have our metric, we can compute gradients, and we can apply the Riemannian gradient descent exactly as we did for the submanifold case. For example, you can perform Riemannian gradient descent on the manifold of frames. That means manifold of orthonormal basis of Rn. So every point of your manifold is an orthonormal basis, for example. Or the manifold of lines through the origin of R3, or k-planes inside Rn, and stuff like that. Now, today we start again from the Taylor expansion along geodesics, just we bring it to the second order, as we did when we introduced geodesics, and we see if we can export other algorithms from the flat case, from Rn, to our Riemannian manifolds. So, let me recall that if you have a geodesic with given starting point P and given starting initial vector, tangent vector V, then for every other point of the geodesic you can write the Taylor expansion like this. So f of q is f of p plus t, and t is the arc length parameter which determines q. T times the gradient, the differential of f evaluated in v plus t squared halves the Hessian of f as a bilinear form evaluated in v plus third order terms. So in general, if gamma is not a geodesic, here you have also a term which depends on the scalar product between the gradient of f and the covariant derivative of the velocity of gamma along gamma, so what you would call the acceleration of gamma. So in general, the last part is something like the scalar product between the gradient of f, well, let's say the scalar product between the covariant acceleration of gamma and the gradient of f and the other term we already have. So now, for a geodesic, this is constantly 0. However, for us, it's enough that this is 0 in P. in f equals 0 at p. So if you want t equals 0. Because, I mean, we wrote the expansion at 0, so the remainder, the second order term will be this whole term evaluated in 0. Now, because this is the second derivative of gamma of t as a function of the variable t. So these are at 0. So if you evaluate this as 0 and this vector at 0 is 0, then you get only the Hessian of f. Now, to clear up things, notation, because we started with these kind of algorithms in Rn, and in Rn, the gradient, the differentials, I mean, they're all the same thing. We defined the gradient on M as nabla M, which was a projection. Now we stopped writing that because we have defined the gradient on every manifold, so we don't need to have a special notation for every Riemannian manifold, so we don't need to have a special notation for the gradient of M on M. So nabla f, the covariant derivative of f, is just the differential of f. The Riemannian gradient is grad f and is defined by this relation. So it's the f sharp. That means that the f applied to any vector field is the scalar product between the gradient of f and that vector field. So it's defined by duality. Likewise, nabla square f is a symmetric two forms on the tangent space. That is, you can apply this to every pair of vectors, v and w, and you get a bilinear form, which is symmetric. Using the metric, like we did above, we can transform it in an endomorphism of the tangent of M. So we define hash of fp, Hessian of f at p, as the linear map which respects this. So it's the linear map which induces the bilinear form through the scalar product. The local coordinates, we're just raising an index, so the Hessian of f at p, the component jk, is this one. So we raised an index by k, which index is not important because the Hessian is symmetric. Okay? Again, this is an Einstein notation, so there is a summation over I understood. And by the way, this just makes sense. So this is at P, this is a map which takes a pair of vectors, tangent vectors, and sends them to a real number. And it's the covariant derivative of the f, in a way. So we didn't really explain what is the covariant derivative of a differential form, but in the case of the Levi-Civita connection, everything is defined through the metric. So, for example, we have that the Hessian of f at p is just the covariant derivative of the gradient of f. Now remember, this is a differential form. This is a vector field. So to pass from one to the other, you have a metric. You have to use the metric. This is the covariant derivative of the f sharp. And if you want to put everything together, the let's call these if you define this one form actually, which is let's say Z. Okay. Which is another way to write the Hessian of f applied to x and y. Now, x and x and z is symmetric, so who cares? Now, this is again a differential one form. So it's a section of the cotangent bundle, and everything works, meaning that this is, let me write this properly, this is the covariant derivative along z of the f sharp, and this will be the vector field, flat. So we raise the index, we get the gradient, we apply the covariant derivative along the field, we get another vector field, we lower the index and we get a form, which is the Hessian with one variable fixed. So everything is related through the metric, so you can just choose the definition you want and remember that you can pass from one to the other by raising or lowering indices. Obviously, notationally, when you do that, you are just raising or lowering an index. So when you write it down in local coordinates in many books and papers, you will just see like x with an I above and x with an I below, but between one and the other, you have applied the metrics. So if you write something like that, you're meaning these. Therefore, they're not the same coefficients just understood as coefficients of something else. They are, in principle, different numbers, depending on the metric G. Now, in Rn, the G and the inverse metric are the identities, so lowering or raising the indexes is, harmless. The same thing we did with the curvature, but I'm not, again, going into that. You have two versions of the curvature, the one with an index above and 3 below, and the one with 4 indexes below. This one comes out naturally from the non-commutativity of covariant derivatives. This one is more easy to write. It's easier to write because it's a linear, is a 4 form on the tangent space. So it's a function that takes 4 vector fields and gives you a number. It's easier to write down, essentially. And they are obtained one from the other with a multiplication by this matrix G. Okay, now, second order attractions. we would like to export on Riemannian manifolds the Newton algorithm. We will talk about it in a while. Now, a second-order retraction is a smooth map R from the tangent bundle to M, or a subset of the tangent bundle to M, etc., such that if you apply R to the point X, the vector 0, you get X. If you fix X and have a map from the tangent at X to M, then the differential at 0 of this map is the identity. And the first two were a first-order retraction. A second-order retraction is this other condition. If you define the curve gamma t equal Rx of TV, so you take this map from the tangent at X to the manifold, and you consider the straight line through the origin, for each straight line you get a curve. Okay? Now, you ask that term, which was bothering us in the second order expansion, so the covariant derivative of the velocity along the curve, at X is 0. We don't care about everything else, just at X. For example, the exponential map. Now, properties. The thing we wrote before holds for f composed with the retraction. F composed with the retraction is a function from the tangent space to R. So it's a function on a Euclidean space. That's the whole point of it. Remember it from lecture 3. It's the same thing. Once we compose f with the retraction with the point x fixed, we get a function from the tangent space to R. So it's a function between Euclidean spaces. We can do everything we want there. We know everything. If you write Taylor at the second order, you get the gradient of, now here G is G on the tangent space, so it's a fixed scalar product. It's not something varying, C infinity, it's a symmetric matrix on the tangent space, because the point is fixed. So we get the scalar product with the gradient and the Hessian written as a linear map. You will see why in a while. We want to think here to the Hessian as a linear map from the tangent to the tangent. So when we, I mean, in Rn is harmless because a symmetric linear form is induced by a matrix, and this matrix gives you a linear operator. So everything is equivalent. Now, the Hessian of f at x is the Hessian of the composition at 0, and which is true also with the gradient. And now, if x is a local minimum, this is not a property of the retraction, it's something we can prove with the curves given by the retraction, or with geodesics, if you want to use geodesics. But in general, it holds true every time we can consider the retraction. So we always have geodesics, but say we don't have them, we don't know about geodesics. If we have a second-order retraction, we can prove this, that in a local minimum, the gradient is 0 and the Hessian is positive semi-definite. By the way, property 1 is true also if x is a critical point for every first-order retraction, because for a first-order retraction you don't have the gradient. For a critical point you don't have the gradient, because the gradient is 0. This term is not here, but also the term from the second order which was bothering us is not there, because it was a scalar product between the acceleration and the gradient of f. In a second-order retraction the acceleration is 0, but in a critical point the gradient is 0, so who cares about the acceleration? Now, a scheme for second-order optimization. Consider a function from the manifold to R, and we have our sequence of points that hopefully are approximating a minimum of f, a minimum points of f. Now, we want to find the next point by approximating f with another function on the tangent space at the present point. So we have x sub k, and we have the tangent space to m at x sub k. We have our function f. We want to write something on the tangent space, and we want to minimize that function. We find the point s sub k plus 1, and we retract it with our xk to this next point. Okay? So why is this a second order thing? Well, because if you just stop at first order approximations for f, you get a linear function. Linear functions don't have a minimum point. So on the tangent space, on a linear space. So that doesn't make sense. We need at least second order expansion. Exactly. So this makes sense only if the approximated version can easily be minimized. Now, write f tilde. Now remember, s is the variable on the tangent. So s is the tangent vector. F tilde of s is f of xk, which is a constant, plus the scalar product between s and the gradient of f at xk. This is a fixed vector, plus 1/2 the scalar product between the Hessian of f at xk evaluated in s times s. This is a fixed matrix. So everything is fixed but s. This is a constant, this is a first degree term, and this is a second degree term in the components of s. So this is quadratic. And if there is a minimum, this minimum is a solution of the following equation, because the gradient of this function is the gradient of f plus the Hessian of f evaluated at s. So you want to find critical points, so you want to find the gradient of f tilde is 0. So you end up by solving this linear equation. The existence of a global minimum is guaranteed by the sign of the Hessian. So if the Hessian of f is positive definite, we know that this function has a global minimum on Rn. Obviously, if the Hessian is not, if the Hessian is indefinite or semi-definite, semi-definite means there won't be a unique minimum, but indefinite means it won't be a minimum. So what's the problem you can easily see here? That in general, our f won't have positive definite Hessian everywhere. This is the convex case, it's easier. The Hessian of f will be positive semi-definite near a minimum point, but not in general. So it depends where we start. Anyway, wishful Riemannian Newton method. This is not the real Newton method. This doesn't work. In almost any case, it doesn't work. But to make it look like a serious thing, it's written like a Python code. Riemannian Newton algorithm. Okay. We initialize everything. And what we do, at every step we solve somehow, this is also a problem we have to address, the linear system with this matrix and this vector of data. We add the new vector because this is the new displacement vector. We apply the retraction. We check if we are close enough to the minimum or not, and we go on. Now, this has a number of, some positive sides and some downsides. Now, the first thing you could notice is here. We don't really have the matrix of the Hessian with respect to a basis of the tangent space, because this changes point by point. So it's hard to compute that. And and sometimes, I mean, you could compute that in an ambient space if you are in the embedded version, but that would be expensive. I mean, computationally expensive, because the ambient space in principle can have a lot of dimensions more. Also, the problem we were saying before, this is not in principle the minimum point of the approximated version if the Hessian is not positive definite. And then there are other problems, but let's start with the good things. Now, if you have a critical point where the Hessian is invertible, so if its positive definite in particular is invertible, the convergence, I mean, there is convergence to this point in a neighborhood, and it's at least quadratic, so it's very fast. And when you're close enough to a critical point, any first-order retraction is enough. So if you have a computationally expensive second-order retraction, you can use that up to a point and then switch to a first-order retraction when you're close enough. Cons. It may not converge. Or it may converge to any, to any critical point where the Hessian is invertible. So if you have the classical saddle point with one positive and one negative eigenvalue in R2, it will converge there. Or it may not converge because as we are not solving a minimum problem on the tangent, if the Hessian is not positive definite, it may jump just around in a aimless way. Even if it converges, you don't know anything about the sign of the Hessian at the limit point. And quite often we don't have the matrix form of the Hessian, so it's difficult to solve the linear system. It's not obvious to solve the linear system. You cannot apply some matrix factorization or stuff like that to the Hessian matrix. So there is realistic corrections. Now, there is a method to from linear algebra that it has nothing to do with the Riemannian geometry, so I'm not explaining it here. You can look it up. I can give you the references if you want. There is a method to approximate the solution of a system where you don't want to, where you don't have the matrix form. So you have the operator form. You can compute the matrix applied to a vector. If you give it the vector, it will. You have a black box, a function, and if you give to it the vector, you will get back the a times the vector, but you don't know a. So there is a method to approximate the solution of AX equal B, which entails the calculation of A times V for some vectors V a finite number of times, actually less than or equal to the dimension of the space you're in. This is called the conjugate gradients method. And there are variations of that which, try to speed up the algorithm, nonlinear gradient conjugate gradients and stuff like that. Now, the big correction, Riemannian trust region method. We don't know that a global minimum exists for our approximated problem. So we have our Hessian of f equals minus gradient of f. But again, if the Hessian is not positive definite, the minimum does not exist. So solving that system is not, doesn't have much sense. So what do we do instead? We minimize the functional f tilde, the approximation, in a small ball around the origin. Doing that still means to have to do with the linear system from before, but not in the same way. This small ball, remember, what is this small ball? Is a small ball in the tangent space. So we have the tangent space of M at P, and we draw a small ball, the vectors of norm less than or equal to epsilon. And it's called the trust region at iteration K. Now we find the minimization there, and then we compare these the gain of the approximated version with respect to the gain of the real cost function. So we have a point xk, we have the tangent space, we have our truss region delta k, and we have our approximate solution sk plus 1. Now, here we have the manifold, and our solution goes down to the next step. So what do? We compare the gain we have on the approximated version with respect to the gain we have in the real version. So f tilde sk plus 1 minus f tilde 0, this is the gain in the approximated version over the gain in the cost function. This is a number, and depending on the value of this number, we decide how to proceed. So if this isn't good enough, we accept the answer. If this is not good enough, we reject the answer we just found. And in both cases, we can change the radius of the truss region. Okay? Obviously, if we reject the approximation, we have to find a new one. But in any case, we change the radius of the truss region for the next step. Okay? So the truss region is where we look for our approximation of the next step. If we take it smaller, it means we are taking smaller steps, hopefully more pointed towards the minimum. Hessian replacement, this is a nice thing. In the first steps, when we are far from the minimum point, instead of the Hessian, we can use almost anything. We can use any operator which is radial, not even linear, and which respects some estimates that we need. When we get closer to the critical point, we need a second-order approximation. So we need things to get good to a second-order point. So, for example, we need the positive definite, or we need a bound on the eigenvalues. So we actually want to approximate the Hessian. But in the first steps, it can be made precise. I mean, you have two parameters which will tell you if you are in the first part or in the second part of the algorithm. But the general idea is that you can replace the Hessian with L times the identity for L a constant, or something which is just radial and not linear, whatever, and it goes all good. When you get close to the critical point, so when the trust region gets smaller and smaller, and your steps get smaller and smaller, you need a good approximation of the behavior up to the second order. So you need the Hessian, also because you need bounds on the eigenvalues, and these should reflect the real behavior of f and not just some random choice. Okay. As in the as in the gradient descent, we have a number of assumptions to make in order for the Riemannian trust region method applied to the Newton algorithm to converge. Obviously, we need to know that our function is bounded from below, and there are some assumptions which are the same from the Riemannian gradient descent. There are some technical assumptions regarding, let's say, having introduced the Riemannian trust region, we don't have just the step size to control, but we have a much more complicated set of conditions. So the sufficient decrease, which was just, okay, every step should have a gain which is at least some multiple of the gradient. That was the sufficient decrease in the Riemannian gradient descent. Now it splits up in a number of different conditions, which are a bit complicated to write down. Well, not really that there are inequalities between two terms, but the notation is annoying, so I won't be going further into that. And then we need some regularity assumptions, like the assumption number 3 in the Riemannian gradient descent, which was a Lipschitz assumption on the gradient. We need Lipschitz-like estimates on the gradient, obviously, and on the Hessian of f composed with the retraction. Now, if we don't have a second order retraction, or if we maybe have a bad approximation of a second order retraction, in any possible case, this term, the estimates on the Hessian of the composition, involves curvature terms. They involve, if you compute the Hessian, you get the Hessian in local coordinates, and another term which depends on the Christoffel symbols, if you remember. It's the Christoffel symbols times the gradient of f. Now, because you compute the Hessian on two directions at a time, two directions at a time, because the Hessian is a bilinear form, you are only applying the other term, now you want the Lipschitz condition on the Hessian. Lipschitz means bounded derivatives, so you are taking the derivatives of terms involving the Christoffel symbols, which will give you, either something terrible and a real mess, or curvature. Now, we don't get real mass, we get curvature. And as we only select two vectors at a time, we get sectional curvature. So for example, if you have a manifold with bounded sectional curvature, you have these estimates once f is nice. For every reasonably well-behaved retraction. Now, an application of this to infinite dimensions. A curve in the plane can be parameterized in many ways. In particular, you can parameterize it like this. You select a starting point, C0. You select R, such that e to the r is the length of the curve. And then two functions. Okay, this e is the exponential. This e is the function, sorry. I should have written exp of r. I will change it later on in the slides. E and g are two functions, and here I'm writing e plus ig as a complex number. So we identify the plane with complex numbers. This is just an integral of this quantity along from 0 to t, depending on the parameter tau. Now, this is, you could ask why. Well, there are a number of reasons. In particular, if we ask that gamma is a closed curve of length e to the r, we get these relations. So e squared and g squared integrated from 0 to 1 give 1, and the product between e and g gives 0. So they form an orthonormal pair in the space of L2 functions. If you don't know what the space of L2 functions is, let's just say that you can put a scalar product on real valued functions by declaring that the scalar product is the integral of the product. So this is the scalar product between e and g for functions on 0, 1. Obviously, your functions should be integrable, at least, and the requirement is that their square should have finite integral, because this will be the norm, square norm of your function. So you see here we say the scalar product is 0, and that the norms are 1, so they're an orthonormal pair. Now, on pairs of orthonormal vectors, you can define a Riemannian metric. In a Rn. They are the 2 times n matrices such that the product of the matrix and the transpose gives you the identity in both orders. So they're a generalization of orthogonal matrices. They're called the Stiefel manifold. Now, this is not surprising. You have at each point, let's say, you have a behavior which is like an orthonormal pair in some Rn. You generalize it to infinite dimensions, and you get a Riemannian metric. You can write it down. Also, in practice, in applications, these 2 functions will just be what? The sampling on the 2 functions on a sequence of points. We will split the interval 0, 1 in, I don't know, 1,000 points, and give for each point the value of e and g. Okay, so they will in the end be a pair of vectors in some Rn with n very big. But to be general, we could give this as a metric on the space of L2 functions. So we have the space of L2 functions is a vector space, and you can give, again, a metric of the orthonormal pairs of vectors in this space. I won't be writing down the metric. Obviously, you also involve C0 and R in the final one, because they will change. An interesting feature of this kind of metric is that there is a closed form from the exponential map. So you can write down explicitly the exponential map. The application. Now, a grayscale image is just a map from the square to R, which gives to every point the gray value, or a function which gives the gray value. Given not a closed curve gamma, and 2 gray values u1 and u2, we consider this functional. A constant a1 times the integral on the internal region enclosed by gamma of u1 minus u squared, integrated in the volume, in the area, a1 plus the integral on the exterior part of gamma inside the unit square, of u2 minus u squared, plus some regularization term which will compute the length of gamma and some other function of the starting point and the length and the whatnot. The functions e and g before. It's a term that guarantees that our gamma doesn't end up being too wild. For example, we don't get a fractal or something like that. So we want to consider well-behaved curves. In our definition, curves can be whatever they want, but we would like to, when we have a practical problem, usually the answer is not a fractal that fills the whole square for every kind of problem. But let's just look at these, at the two main parts, which are this and this one. So this function is minimized when gamma borders a region of mean color U1 and leaves out a region of mean color U2 with small variance, meaning that the region should be more or less uniformly of color U1 and the other should be more or less uniformly of color U2. This term guarantees you that gamma is not too wild. Is a nice curve in a way. Minimizing F means to perform an image segmentation in parts of given color. So, given an image, we can more or less guess, taking means and stuff like that, what the main parts, what color will the main parts of the image be, and we try to write down these functional or more complicated versions of this functional with many pieces of curves enclosing different regions, or just iterating these on the remaining parts of the image to divide gamma into pieces of similar mean color. Now, what can you do? You can preprocess, you take an image, you preprocess it, well, you convert it to grayscale, but this is not important. You can do that on the 3 RGB levels, for example. You convert it to grayscale, then you somehow smooth the, well, not really. You flatten the parts where the variation of the color is very smooth and let's say with mild gradient, and you enhance the parts where the color changes sharply, the edges. There are like easy methods to do that for image manipulation. You are essentially applying a convolution matrix to the image. And then you apply this algorithm. What you get is an image segmentation procedure. So for example, you start from here with this circle, and you can get your algorithm to slowly approximate. This is the most poorly performing algorithm of the various possible. This is the pure Newton method with the Riemannian trust region. So you see it lefts the head off and stuff like that. But if you get, I mean, you can do more complicated versions of the algorithm. You can improve various parts, and you can get even better results. These are not too many iterations. I don't remember, but I mean, like 100 iterations or something like that. So that's a quite good job. And there are, with these kind of interpretations of curves as a pair of functions with some relationship among them, there are a number of applications to 2D shape recognition or handling curves in 2 dimensions and so on. Just a side note, we mean people who do that do not use the standard L2 metric on function spaces of like functions from R to R2, because these metrics usually degenerate. I mean, there is a metric which is canonically linked to the L2 norm, but this is a degenerate metric, so you will usually get curves of infinite length or curves of 0 length or stuff like that, stuff you don't want, or curves which are really far from being smooth. Okay, I think it's enough about that.